Okay, hi everybody, let us start. So, as a reminder, please feel free to turn on your video, or you're encouraged to do so, because I need to look at the faces. And also I'm going to have office hours tomorrow, so office hours Thursday at 12 p.m. I think. It's in the syllabus, the Zoom link and all the details in the syllabus, which is on CCLE. Okay, a few more faces. Nice, thanks. All right, so last time I was talking about these, and also by the way, so you can, if you have any questions, you can come into the office hours, but you are also encouraged to just send me an email. I am going to be happy to respond to all the emails with the questions about homework or life or whatever. Okay, so let me remind you what we did last time, and basically I didn't do very much, but what I did was, first of all, I defined injective, surjective, and bijective maps. So if you have a map F from between two sets A and B, then F is injective if it sends different elements to different values, and it is surjective if the image is the whole set B. Surjective if let me just write it. The image of F is the whole set B, where the image is just the set of all values of your map F. And finally, it's bijective if it is injective and surjective. So it sends each element to A to a unique element of B, and each element of B is covered by a unique element of A. And then I defined permutations using this language. Permutations are just bijections from bracket n to itself, where bracket n is 1 to the integers between 1 and n. So for example, when n is equal to 3, then the permutations are basically, well, I have bracket n is 1 to 3, so I have to set 1 to 3 to 1 to 3 in some way. So I can do this in 6 different ways. Let's see if I can do this successfully, to just draw 6 permutations. Yeah, okay. So 1 to 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. Yeah, these are the 6 possible bijections. All right, so that's the previous material, and then I also did some more complicated stuff, which I'm not going to need anymore. So any questions on this stuff or any other logistical stuff? Okay. No questions. All right. So today we want to, there was one more point, which is that the number of permutations is n factorial. Number of permutations is n factorial, which is 1 times 2 times etc. times n. And so today we're going to count some slightly more complicated objects than permutations. And so the answers are going to be slightly more involved. And I'd like to start with an example. So this example I actually like from the book, so let me try to explain. It's a sports analogy. Recording, okay, yes. Somebody's asking whether I'm recording. I'm not recording via Zoom, but I'm using my own thing running in the background, which hopefully will, yeah, sometimes it does not work, so sometimes I have to re-record the lectures, which is weird, but hopefully this time it works. Yeah, but yeah, thanks for the reminder. All right, so the question is from sports is that you have n runners. N runners, let me denote them by maybe R1, R2, etc. R sub n. They participate in a race. Question? No. So they start running, and then there's the finish line. So they finish kind of in different orders, and then eventually we're gonna give them medals, like in the Olympics. So maybe so you have 3 different runners which win these gold and silver and bronze medals. So do you mind if I mute, because I can hear feedback? Yeah, let me just, okay. Yeah, if you have a question, please feel free to unmute. All right, so you have 3 winners. One is the gold and the silver and the bronze winner. So the question is how many medal winner lists can we get? So in how many different ways can the list of winners look like? Any ideas? What's the answer going to be? Okay, thank you. N times n minus 1. The answer is n times n minus 1 times n minus 2. Because, well, yeah, for the gold medal winner, basically anybody can get the gold medal, and then so that's n options for R sub A, and then n, because one person cannot win the gold and the silver medal, there is n minus 1 options for R sub B and n minus 2 options for R sub C. Okay, this is nice, and then let's generalize. So in general, let's say you have not, here we had 3 medals. In general, we're going to have k different kinds of medals. Oh, n factorial over n minus 3 factorial. Yeah, that's also a, so this is equal to n factorial over n minus 3 factorial. That is also true. Okay, so in general, yeah, so if you have k medal winners, then you can continue this argument. So we have basically shown the following proposition, which is that which involves the number of ways to, yeah, in words it sounds kind of clunky, but let me write it down. So for k less than or equal to n, the number of ways to make a partial, well, number of ways to make a partial list of k elements of bracket n is equal to, so here, yeah, I guess partial list is not very good terminology, but it's, yeah, just make an, let me write, make an ordered list of k elements without repetitions. So that's the condition that the same person cannot win 2 different medals. So this, yeah, and this number of ways is equal to n times n minus 1 times n minus 2, etc., all the way up to n minus k plus 1. which is the same as n factorial divided by n minus k factorial. And so I'm going to denote this number by these parentheses n sub k. So that is called a falling factorial. Yeah. And yeah, hopefully it's clear. Is it clear? Let me know. Is there any questions on how to prove this proposition? Okay, no questions. So here is a question I have. Question: how to basically how to restate this problem and this number in terms of injections, surjections, and bijections. So is there, you see I struggled to say this in words, an ordered list of k elements without interpretations. So what would be a name of such an object in using these three smart words? Okay, injection from bracket k to bracket n. Thank you, that is correct. So the answer is that this falling factorial is the number of injections from bracket k to bracket n. All right. Yeah, so, and that's, this language has the advantage of being precise. Otherwise, you have to say these long sentences, whether you allow repetitions or not allow. So it's useful to kind of understand how to use both languages, because sometimes it's more convenient to use the other one. All right. Now, I guess now what I'm going to do is I'm going to explain there's going to be some very basic counting principles. Counting principles. And so there's going to be 4 of them. And yeah, they're going to correspond to addition, subtraction, multiplication, and division. So if you open the book, then it starts with like, when do we add things? And it sounds really basic, but I'm going to use it to introduce some terminology and maybe explain a few simple tricks that you can use. So yeah, here is the addition principle. Addition principle, again, sounds super basic, but so if you have 2 sets A and B which do not intersect, so A and B are disjoint, then the size of their union is equal to the sum of their sizes. Where, yes, so you see I'm using not the curly union in the curly cup, but like a square cup. That's called, I'm going to use that when I want to emphasize that it's disjoint union. And okay, so this is really an obvious statement, but oh, sorry, yes, thank you. A cap B should be empty. Yes. So when you use it, if you want to count, usually you have to count a bunch of objects, and then you have to consider some cases, right? So maybe some runners finish the race, and some runners don't finish the race. So you have to, whenever you have to consider 2 disjoint cases, then you're going to add up the answers, and usually, in many problems, you're going to have to consider at least a couple of cases. And it's usually, yeah, so the game is always to kind of figure out the way to split into the cases such that there's not too many of them. And yeah, and then you just add up the answers over all these different cases. So yeah, that's the addition is the easy one, I guess. But the subtraction one is, it also sounds easy, but let me, okay, subtraction principle, which is that if my two sets are, if B is contained inside of A, then the size of the set difference, A minus B, is equal to the size of A minus the size of B. So here, again, this is notation for set difference, which just by definition is the set of all elements in A which are not contained in B. And in the book you're going to see also denoted A minus B. So if you read math papers, then most people, I would say most people use this notation, but some papers, especially in kind of more geometric sciences, they use just A minus B. So yeah, I think I'm gonna stick to this one because I don't want it to be confused with the minus of with the difference of numbers. All right, and so why is this principle useful? It's useful when you want to compute this, the size of difference, but it's easier to, instead of computing it directly, it's easier to compute the size of A and the size of B and then just subtract. So again, an example from the book, which I think is very nice, is, so here's a question. Here's a question, how do we count how many positive integers which are, so they have to be positive and at most 1,000. How many of them have at least 2 different digits? Any ideas? Yeah, so for example, 1,000 has 2 different digits, 1 and 0, but 999 only has 1 digit. So how do we count these? Okay, 1,000 minus 9. So 1,000 minus 9 minus 9 minus 9. Okay, because digits and 1 digits. All right, yeah, that's actually correct. So the answer is 1,000 minus 9 minus 9 minus 9, which is 973. And the reason is that if you set the set A to be all integers between 0 and 1,000, and B to be all the set of all numbers between all positive integers at most 1,000 which consists of a single digit, consisting of a single digit. And then yeah, so B is basically the set of 1, 1, 2, all the way up to 9, and then 11, 22, all the way up to 99, and finally 111, all the way up to 999. So that's B, all right? And in particular, the size of A is 1,000, the size of B is 27. So and now you use the subtraction principle to count the answer. Which you can try doing this by hand without the subtraction. Without the subtraction, it's kind of hard because you have to count two-digit numbers and then 3-digit numbers, and it's complicated. It's not completely clear how to do this, but the whole problem is made much easier by just subtracting these two. Okay, Now, and that's the trick you can use a lot in the common problems. So you have to be, sometimes you have to be clever and subtract. That's the moral. Any questions? Okay. Yeah. So the next one is the product principle, which is that, I guess here, yeah, the size of A times B is equal to the size of A times the size of B, where so by definition the Cartesian product of two sets is the set of all pairs A comma B, where A belongs to A and B belongs to B. That's the product of sets. And then, of course, if you want to count the number of ordered pairs, an element of A and an element of B, then the answer is going to be the size of A times the size of B. And okay, so I guess I can maybe give you one example or even a couple of examples. So let's count some other numbers. So yeah, let's say I want to count the number of numbers, the number of positive integers with exactly k digits. Number of positive integers with exactly k digits is okay. Question: Are A and B disjoint for product principle? No. So A and B, any two sets, not necessarily disjoint. So when you consider these ordered pairs, it's the order matters. So maybe I should write down an example. So let's say I take bracket 3 times bracket 2, and what I get is the set of pairs, which is going to be 1, 1, 1, 2, 2, 1, 2, 2, 3, 1, and 3, 2. So you can see I have 1, 2, and 2, 1, and I consider them to be different pairs. And the total number of elements is 6, which is 3 times 2. Okay, thanks. All right. So does anybody know how many positive integers with k digits are there? Okay, 9 times 10 to the k minus 1. Okay, that's true. Thank you. 9 times 10 to the k minus 1. And the reason is that if you have your k places, then the first place has to be non-zero, so it has to be a number between 1 and 9, so it has 9 options. But then all these other places can have any number, any digit between 0 and 9. So there is k minus 1 spots where there is 10 options, but for the first spot you only have 9 options. And then because any combination would work, you kind of iterate this rule, the product rule, to just multiply the numbers of options. And it's kind of similar to how we computed n factorial. And yeah, let me also mention another much more useful fact, which we're gonna need later, is that if you just look at all, so here it mattered that the first number is non-zero, but in general we're gonna consider sequences of arbitrary words in k letters. So the number of k letter, well, okay, I guess I have to number of strings with k letters from n letter alphabet is equal to just n to the power of k. So yeah, again, you have the same, you have k spots, but then each spot can contain an arbitrary letter. So n is like 27, like just the size of your alphabet. And another, so an alternative way to say the same thing is that if you take bracket n and you take it to the power of k, which just by definition is you multiply it as a set by itself k times, then then the size of this set is going to be equal to n to the k. So this bracket n to the k is literally the it consists of all strings of length k where every letter has n possible options. Okay. Yeah, and any questions on this one, by the way? All right. So finally, the division principle, which this is something we're going to use. Actually, this one is very tricky to use. If you use it wisely, it's very powerful. So the division principle, it tells you the following thing. So if you have a d-to-1 map, so first definition for if you have some positive integer d, a d-to-1 map is a map f from A to B such that for any element in B there's exactly d elements in A that map to this element. For any B in B there are exactly d elements of A that map to B. Okay, so the picture you should have in your head looks kind of like this. Here's your set A, here's your set B. You have some points here and then some points here. So I'm going to draw a picture for d equals to 2, I guess. Right. It's going to be exactly d elements that map to each given element of B. So in particular, any d-to-1 map is surjective. Any d-to-1 map is surjective. All right. So yeah, and I guess I have to give you a warning, because the warning comes when d is actually equal to 1. When d is equal to 1, then notations and conventions actually differ. So warning. When d is equal to 1, then different people mean different things. Things by a 1-to-1 map. 1-to-1 map. Which, okay, so the two options are some people mean injective and some mean bijective. Okay. So the most common meaning for the notion of a 1-to-1 map is an injective map. But if you just literally take this definition and apply it, right, for each B, there's going to be exactly one A that maps to B, so you get a bijective map. So in order to avoid confusion, I'm going to, for d equals to 1, I'm not going to use this definition above, but I'm going to just use the words injective and bijective to just make sure. Okay, are we going to use one-to-one as injective or bijective? Yeah, I'm just going to not use one-to-one. Yeah, that's a good question. Whenever I see it in a paper, I always have to guess, because like all people in Russia use it as bijective. So whenever I see a Russian person write a paper, I have to assume it's bijective. Yeah, anyways, it's a mess. But yeah, for this class, let's say it means injective, because in the US, I guess it still depends. Anyways, it depends on geographical constraints. All right, yeah. This definition is only useful when d is strictly bigger than 1, because then you can apply a division principle. But what is the division principle? Division principle. And if you write it in a homework, I mean, we're not gonna penalize you for kind of bad terminology. As long as David understands what you wrote, you should be fine. Yeah. We're only gonna penalize the substantial mistakes. All right. So division principle is that if you have a map from A to B, which is a D to 1 map, then the size of B is equal to the size of A divided by D. You should keep this picture in mind. So the size of B is going to be smaller than the size of A obtained by dividing it by D. So again, all I'm saying is very, very trivial, but the applications are what makes it non-trivial. And what you usually use it for is when you know the size of A and you want to find the size of B. So it's kind of a trick by, there's like a joke about some mathematician which comes, I don't really like corny jokes, but this one is directly relevant. Right? There's like a mathematician which goes to a farm and counts the number of cows in the field, and they ask him how he did that, and he said, I just counted the legs and divided by 4. So that's literally, you count the legs of cows, and then you divide by 4, and that's the division trick that you use. So yeah. Okay, so how do you apply it to problems? So let's consider another problem, also from the book. So let's say you have a circular table with n chairs. And the question is, how many ways to sit n people around a circular table? And I guess I have to say when do I consider 2 sittings equivalent, and when two sittings are equivalent, so they count for 1 if and only if they differ by clockwise rotation. Okay, there is an answer, n minus 1 factorial, n minus 1 factorial. Okay, yeah, that's true. The answer is n minus 1 factorial. And how do you see that it's n minus 1 factorial? N factorial divided by n. Okay, yeah, that's a good explanation. So it's n factorial divided by n. So in other words, how do we get here? You have to tell me what is A and what is B, or maybe I have to tell you. So the set A is just the set of all permutations of so permutations on n letters, right? If you let's say have some permutation 5, 2, 3, 1, 4, 6, something like this is your permutation. And then so B is these permutations modulo this equivalence relation. So modulo clockwise rotation. So an element of A looks something like this, and an element of B looks something like this. 5, 2, 3, 1, 4, 6. So I kind of forget where the instead of having this linear arrangement, I have a circular arrangement, and I just forget where the circle breaks. So in particular, every circular arrangement can come from n different permutations by virtue of you can just pick any of the n spots between two people, and you can break. Right, you can if you break it here, then you're going to get 6, 5, 2, 3, 1, 4. You're going to get another permutation. And in general, there's going to be n different permutations which map to the same circular arrangements. So yeah, that's the division principle at kind of at a nice application, which, I mean, yeah, let me discuss a somewhat more complicated application of the same division principle, which is I'm going to use it to count binomial coefficients. Any questions so far, by the way? All right, no questions. Okay, so binomial coefficients count k element subsets of bracket n, which, so how many k element subsets of bracket n are there? So remember, a subset means that we choose k elements as we did for partial lists, but we disregard the order. So for example, yeah, set of 1, 3 is equal to the set 3, 1. You disregard the order. These are both of these are the same kind of two-element subset of bracket n. So you ask, well, okay, how many? Can somebody tell me, by the way, how many k-element subsets of bracket n are there? Okay, I see the correct answers in the chat. Okay, the answer is n choose k. The answer is n choose k, which by definition is n factorial divided by k factorial times n minus k factorial. Okay, so for example, 4 choose 2. Let's see. 4 choose 2 is 4 factorial divided by 2 factorial times 4 minus 2 factorial. So 1 times 2 times 3 times 4 over 1 times 2 times 1 times 2. And yeah, the answer is 6. And if you look at two-element subsets of bracket 4, then you're going to see sets 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, and 3, 4. So there is 6 of them. All right, so proof. I mean, I have to prove it. I cannot just state this formula. So how do I prove it using the amazing principles I just explained? Okay, division principle. We have n factorial total and then have to use division principle. Same as number of objective functions from k to n and then divide by k factorial. Oh, okay, that's okay, thank you. Yeah, that the right. You have to use division principle, but you have to be kind of clever. So I'm gonna use what I already, as you remember, at some point I computed the number of injection, the number of partial lists. So the number of injections from bracket k to bracket n. All right. So number of injections from bracket k into bracket n is equal to the following factorial, which is n times n minus 1, etc., to n minus k plus 1, which is n factorial divided by n minus k factorial. For n factorial permutations, we select the first k elements and we get a unique first k elements. Okay, all right, yeah, that's also correct. So yeah, I guess there's two different proofs. One is okay, so let me finish the first proof. So you take the number of injections, which is given by this ratio of factorials, and that gives you a way to choose a partial ordered list of k elements of bracket n without repetition. So all you have to do now is you forget the order. Forget the order, and this way you get, and so by forgetting the order, I mean I just look at the images of the first k elements, of these k elements here, and then I forget their order, so there is going to be k factorial. You get a k factorial to 1 map between two sets. So A is the set of all injections from bracket k into bracket n, and B is the set of all k element subsets of bracket n. So the map from A to B, which consists of forgetting the order, is d to 1. So the size of B is the size of A divided by k factorial, which is d, right, as in d to 1 map. So the answer is n factorial over k factorial n minus k factorial, and that's the end of the proof. Or yeah, another proof would be if you take a permutation, maybe 5, 2, 3, 1, 6, 4, 9, 7, 8. Yeah. And then, so let's say n is equals to 9 and k is equal to 4. So then what you do is you forget the order of the first k elements and the last n minus k elements. So you kind of, in this case, k is equal to 4, so you basically you discard the last elements altogether, and then you just forget the order, so you get 1, 2, 3, 5. You get a k element set. And so this way you get because you have to forget the order here and also the order of the remaining elements, you get a k factorial times n minus k factorial to 1 map from the set of permutations to the set of k-element sets. Okay, and then you divide and you get the same answer. And so, and kind of a pretty hard exercise is to show that n factorial over k factorial times n minus k factorial is an integer. Yeah, we showed that it counts the number of k-element sets, so it must be an integer. But I guess, how do you show it directly? Without, you have n factorial, how to show that it's divisible by k factorial times n minus k factorial. That's a pretty non-trivial exercise. All right, so any questions so far? All right, no questions. Yeah, then I guess the last thing today that I'm going to mention. So today is a very introductory lecture. So I want to mention the binomial theorem, which maybe some of you learned from high school, but it's also useful for combinatorics in unpredictable ways. So it's called the binomial theorem, and I'm only going to use it for the integer powers. So for an integer n, for n an integer, positive integer, if you take x plus y to the n, then it expands as a sum of n choose k, x to the k, y to the n minus k. So for example, as you all know much better than me probably, x plus y cubed is x cubed plus, so I have to compute 3 choose 1, I have to 3 choose 0, yeah, okay, let me first write it down. 3 choose 0 times x cubed plus 3 choose 1 times x squared plus 3 choose 2 times x cubed plus 3 choose 3 times, whoops, it should be x, and this should be 1. And I have to multiply by powers of y, x squared y, x y squared, and y cubed. Right, and if you compute these binomial coefficients, then you get x cubed plus 3x squared y plus 3xy squared plus y cubed, because n choose 0 and n choose n are always equal to 1. All right, there's a unique 0-element set, a unique n-element subset of bracket n. So and maybe, okay, I have 2 more minutes. Then let me mention, this theorem is, yeah, I'm not going to prove. It's very easy to prove, right? You just, okay, yeah, I can even prove it. Proof, you just write x plus y to the n as x plus y times x plus y times etc. times x plus y. So you have a product of n terms. And so if you expand this product, then you can, from each bracket, you can choose either x or y. So you basically have these strings on an alphabet of 2 letters. And the coefficient of x to the k, y to the n minus k corresponds to, you have to pick k brackets where you choose x, and then you choose y in the rest of the brackets. So, and that coefficient is exactly n choose k, just because of this observation that you have to pick x and y. Yeah, I think I'm basically done for today. So if you have any questions, let me know. If not, next time I'm going to explain quite a few applications of the binomial theorem to counting. All right, thanks.